Assalamu alaikum rahmatullah. Hello guys. Today we will talk about linear algebra. Linear algebra is amazing topic to talk, and there are many different kind of terminologies in the linear algebra, and sometimes honestly I also forget some of terms, and maybe I also somehow misunderstand some kind of parts also. And it's normal, it's natural. And today we will talk about linear algebra, which is useful for deep learning. Assume if this is linear algebra, we will talk only specific part of this pi, linear algebra pi, which can be relevant and important for deep learning and understanding deep learning algorithms. So let's get started. Okay, screen. Okay, I think you can see my screen. So, linear algebra. We will cover chapter 2 of deep learning book. Yeah, so we will talk about important part of linear algebra and its applications regarding to deep learning. So first of all, scalar values. Scalars. Scalars are single number, single elements. They can be real number, rational number, integers, and etc. And we denote them as lowercase and italic letters, so like maybe a or x or maybe m, etc. That is scalar. That's simple. Second thing, vectors. Vectors is a 1D array, so we denote vectors as lowercase also. They are also lowercase, but they are bold. So if I will give it x, it should be bold. In academia we do like that. So it's agreement. So maybe if x equal to 1 and 2, it means that our 1D array of elements, array of numbers, and the length of these elements is 2, and this vector is 1D. And we can say that vectors consist of scalars. And notation, yeah, example notation for type and size r, and n is the length of vector rn, where n equal to length of the vector. So okay, that's clear. I think very easy, like maybe like kindergarten kid can also understand. Next thing, matrices. Matrices is 2D array of numbers, and we denote them as uppercase letters, like for example a equal to 1 1 3 4. So this is 2D array of numbers, and we denote we give notation as r m to n, where m is number of rows and n is number of columns. So in our case is that a equal to r 2 by 2. That's clear, right? That's matrices. It's just 2D array of numbers, vectors 1D array of numbers, scalars is 0D array of numbers. It means just numbers. And then next term is tensors. I'm sure that you have heard about tensors in PyTorch, in TensorFlow, and other places. So tensors is used for higher dimensional. So matrices deals with 2D. They deal with 2D. Vectors deals with 1D. Scalars deals with 0D, and tensors can deal with 3D and more. And also Also, tensors can be scalar, can be vector, can be matrix, and more. So they are kind of unique citizens of linear algebra. And usually when we deal with linear equations and other equations in linear algebra, we use matrices and vectors. And tensors are more about like dealing with higher dimensionalities, and it's just for practice, just for machines to do calculations. And basically matrices is good for practice for now. So that's all about simple terms, about scalar, about vector, about matrices, about tensors. So importantly is that you should think that vectors, and if you can differentiate between vectors and matrices and scalars, that's good. Tensors are everything. Citizens. Good citizen and unique citizen. So next one, matrix transpose. One of the most important thing is transpose, matrix transpose. It's very useful. So matrix transpose is just taking this matrix and flipping around. Matrix flipping around. It means that the values in column goes to row and values in row goes to column. So let's look to this example. So elements in diagonal part will stay at the same place, but you can see that A21 goes instead of A12. It's like this is matrix. Assuming this matrix, it goes like this. All elements is becoming like changing the places, changing the seats, and that is transpose, matrix transpose. Official like code, like formula for that, maybe like okay, just a moment. Let's be professional, and that we should use the same color. Yeah. So AT of I and J equal to A, J, and I. So that's transpose. So simply, if someone asks you what is matrix transpose, matrix transpose is flipping around the matrix horizontally or vertically so that the places of each element changes symmetrically based on the diagonal. That's all. And as we are dealing with linear algebra, that we can say that A B transpose equal to A transpose. Yeah, it's a B transpose and A transpose. So next thing, matrix product. So matrix product. So it is very easy, I can say. So let me to show you one example. For example, let's first calculate with matrix and vector. Assuming we have 1, 2, 4, 5 matrix. So it has what? It has 2 by 2, right? This shape of matrix. And we will multiply this to vector 1, 2. I'm using these very small vectors and matrices in order to calculate efficiently. So here it is 2 by 1. 2 stands of number of rows, 1 stands of number of columns. Here it's 2 by 1. Here 2 by 2. So in the end, we will receive 2 by 1. If you ask me how you figure out that in the end you will get 2 by 1 vector, it's thanks to formula. So we have formula m by n multiplied by n by p. Assuming like that, in order to multiply one matrix to another matrix, they should fit. So we cannot multiply any matrix to any vector or any another matrix. They should fit. Number of columns of first matrix should fit with number of rows with another matrix or another vector. So in this case, we will receive m by p. So that's what we are getting. 2, 2, 2, 1. So in the end, like this one goes, and we only get m by p. It's 2 by 1. So what we will do here is that we will multiply horizontally and vertically. Horizontally and vertically. So what we are receiving? 1 multiplied 1 plus 2 multiplied 2 multiplied 2. And we are receiving 4 multiplied 1 plus 5 multiplied 2. It means that 1 plus 4, 5. 10, 14. Okay. So that's what we are receiving. That's matrix multiplication. And it is dot product. So it's for vectors, and assume if we will do matrix to matrix, it's dot product. There are two things. There are multiplication and dot product. Dot product is like what I am doing is dot product. So let's give like 2 by 2, 2 by 2. So we are multiplying 2 by 2 matrix, 2 by 2 matrix. In that case, the same logic. So first let's find the shape. 2 by 2, we are getting dot product of 2 by 2. So in the end, we will receive 2 by 2. So this first element is equal to first row multiplied to first column multiplied to first row. Okay, so what it will be? 1 multiplied by 2, 2, 2 plus 4, 6. So if I delete, so it will be 6. Second one, in order to find this value, we need to multiply this row to this column. So it's the same, it's also 6, right? 6. And the same process for the second row. So we will multiply this one to first column and to the second column to find second. So it will be 4 by 2, 8, 8 plus 18. And then it's also 18. That's all. That's how multiplication, that's how dot product works. If we will do multiplication is another thing. If we do multiplication, 1, 2, 4, 5, multiplying 2 by 2, 2, 2. We will multiply this one to this one, this one to this one, this one to this one, this one to this one. But it's not useful, and it's not what we are looking for. Sometimes people misunderstand that things, but we should clearly differentiate between dot product and matrix multiplication. That's about matrix dot product. Next thing, very important thing, identity matrix. Identity matrix is matrix where diagonals have value of 1 and other than that 0. And identity matrix are always square matrix. So we give identity matrix notation of I, and maybe like 2, and it will be 1, 1, 2, 0, 0. I of 3 is 1, 1, 1, 0, 0, 0, 0, 0, 0. What if we use identity matrix? Identity matrix is very useful. They are easy, right? Like in diagonals it is 1, other place it's 0 0. If you multiply this identity to another matrix, it's very easy to calculate. You should know that identity matrix. And that's all about identity matrix. So we should open new page. Okay. How can I do new page? Okay, I should figure out how can I add new page. Page settings, add to, text, save, print. Okay, I am adding new pages. That's good. We figure out how to add new page here. Okay. We talk about identity matrix, and then we will talk system of equations. So we have equations, assuming that there is matrix A, and there is vector X, and there is B vector. And there is a system of equations. For example, A1x equal to B1, A2x equal to B2. So it's equation, system of equations, and where we are given matrix of A, and we are given the B vector, and we should find x vector. And how can we find this x vector? So in linear algebra, now you will see the magic of linear algebra here. So in order to solve this system of equations, there are good and easy way of doing that, and that is doing by matrix inverse. Before talking about matrix inverse, let's talk about what can we have as x. As x, yes, solution. So this linear system of equation can have no solution at all, a lot of solutions, and exactly one solution. And why we are using this matrix inverse? And matrix inverse is, we call it is A minus 1. And it's sometimes expensive, very expensive to calculate inverse of matrix. But if you know inverse of the matrix, then solving the equation of this type is not a problem. Because according to the formula, A multiplied by A inverse equal to identity matrix. It is dot product, dot. And if we know that it is identity matrix, we can say that AX equal to B. We will give both sides A identity inverse of A, which means that A inverse of A and X equal to A inverse and B. This gives us identity matrix, and it is A minus 1 B. Identity matrix is that we can just skip it, and that if we want to find x, that we need to get dot product of inverse of A and dot and with B vector. In that case, we will receive X value. So you can see that finding X is easy if we know inverse of A. So one of the usage of inverse is in inverse matrix is that we can find and solve these equations, linear equations. And let's talk about next thing. Invertibility. Matrix cannot be inverted if more rows than column, more columns than rows, redundant row, columns, linearly dependent, low rank. Okay, I think it doesn't make sense good. A lot of so next thing. Norms. Norms is defines the size of the matrix, a size of the vector. And in order to find norm, it means finding the length of the vector. And there are many different kind of norms, but basically this is a formula of the norm. We have L1 norm, we have L2 norm. L2 norm is Euclidean norm. L1 norm I don't remember clearly. And there is also max norm and other. So it's just useful for finding the length of the vector. What is the length of the vector? And these norms are usually comes in ridge regression and in classical machine learning algorithms. That's what I can tell about norms. So next, special matrices and vectors. Let's talk from the down to top. Orthogonal matrix. If you have matrix and if it is orthogonal, it means it's very easy to find inverse of that matrix, because we are saying that A inverse is equal to A transpose, which means that if we have A, if we transpose it, we will get inverse automatically, which means that we can then solve this linear system of linear equations easily and very cheap, and we will not spend a lot of computation. And the matrix which has, if you have matrix and if it is orthogonal, it means that you will have the very cheap computation and very you will find inverse of that matrix easily. Symmetric matrix is that A equal to AT. That's all. I don't have another comment for that one. And unit vector. So it means that unit vector is length of this X vector is equal to 1. This 2 notation, this 2, it means norm. If norm L2 norm of this X is equal to 1, then we call it unit vector. Okay, now very interesting topics. Time for very, very interesting topic, and we are in good timing, I think. Eigen decomposition. Eigen is, if I don't mistake, it is German word, and eigen means own or proper decomposition or own decomposition. And we use eigen decomposition for data analysis and principal component analysis. And decomposition means that there is A matrix, and we can decompose this A matrix into eigenvectors and eigenvalues. Instead of representing this A matrix, we can decompose it and make it smaller. It's the same, like, for example, 12 is what? It is 2 2 square multiplied 3. So we are decomposing this 12 into the two elements. So the same logic is for matrix. So we have a matrix. So we are decomposing it into eigenvectors and eigenvalues, so that if we have A and if we give that vector to the A, we will that this one is equal to the vector plus with some values, with some eigenvalue, so that we can decompose this one, especially this one, into the eigenvector and eigenvalues. So one matrix can have many eigenvalues and many eigenvectors. And eigen decomposition works only for square matrix. Square matrix means 2 by 2 matrix or 3 by 3 matrix, but it won't work for 3 by 4. And yeah, that's about eigen decomposition. So it's saying that every real symmetric matrix has a real orthogonal eigen decomposition. Okay. Next thing, effects of eigenvalues. So assuming that we have this vector 1, vector 2 to this vector, and if we multiply it, it changes the shape, its shape, but it doesn't change its direction. So it's like it becomes more and more, but like the value is becoming more, but the direction won't change. That's about eigenvalues. So it means that we can decompose. So in the end of the day, what's the usage of the eigenvalue decomposition is that we can decompose certain metrics, certain information into the smaller informations, and we can represent this information as these small parts, as the small vectors and eigenvalues. So this eigen decomposition works only for square matrix. However, but for non-square matrices, we are using the logic called singular value decomposition. So in here we are decomposing the A matrix into these elements U, D, V, and T. So what is take out from here that singular value decomposition is used not for square matrix. So if matrix is square, we can go for decomposition to eigenvalues. If matrix is not square, assuming it's 3 by 4 matrix, so we then, if we need decomposition, we will go to singular value decomposition part. So that's how singular value decomposition works. Next one, Moore-Penrose pseudo-inverse. Pseudo, I will write. Pseudo means false. So not every matrix has inverse. Only square matrix has inverse. At some point we need values close to inverse, and sometimes we need that inverse values even though we cannot get inverse of that matrix. And there was one formula about that pseudo inverse that's a bit complicated, that as a goes to 0 and a transpose to a plus that alpha to identity matrix, and etc and etc. But instead of diving to that formula, let's go to next one of computing that pseudo inverse. So for non-square matrices, to find inverse of that matrix, false inverse, not true inverse, just false or similar to that inverse, we can use singular value decomposition values. So singular value decomposition is used for non-square matrices, right? And pseudo inverse finds inverse of that non-square matrices. So by using the elements of SVD, singular value decomposition, we can find this A plus. So A plus is nothing but the pseudo inverse, is equal to this V D plus and UT. And by that we can find that inverse. So as we said, why we need inverse? If we have inverse, we can solve the system of linear equations very cheaply. And there are other usage also, but mostly for that case. Okay, trace. Trace is, so we can, if we go to formula of is here, it's clear what is trace. There are many other definitions in linear algebra. There are like I think you have heard about determinant, other thing. So here, what is trace? Trace is sum of diagonal elements I and I, assuming if A is 2 by 2 and it is 2 2 2 6. So our trace of this A is equal to 2 plus 6 equals 8. That's about trace. And it's saying that trace of ABC, trace of this matrix is equal to trace of CAB or trace of BCA. So they are equal. And actually, I think that's all for today. So that's all what you need to cover about linear algebra in terms of deep learning. And of course, if you need to understand more deeply, you should again recheck and read more deeper book focused on that part of linear algebra, because even though if you read more about linear algebra and if you don't do enough practice, it is natural that you may forget some terms, and that may be not what you want. So overall, we talk about what is scalar, what is vectors, and some and we talk about matrix inverse and transpose, and what is identity matrix, what is trace, and we talk about how to solve a system of linear equations, and how useful if we have inverse of A, and that if matrix is square, if we need to decompose, we will use eigen decomposition. If it's not square, we will go to singular value decomposition. If we need to find the inverse of the matrix and it is not square, we will go to pseudo inverse. If we need to find inverse of the square matrix, we will use designated formula for that and find that inverse. And sometimes it's like a bit expensive to calculate the inverse, but generally it's not big deal. And now here, as a author of book, is recommending that to do a lot of practical problems, and then start out with lots of summation, science and indexing into individual entries. Eventually, you will be able to mostly use matrices and vectors products notations quickly and easily. So that's about linear algebra quickly. I think that's all. And if you need to read more, please go to deeplearningbook.org and check the chapter 2 and read chapter 2 entirely. It might be boring, it might be not fun at all, but find time and please read it, as getting more and more better understanding of linear algebra. Linear algebra indeed is great topic to discuss, and later when we will do a lot of deep learning related practice, we can see the real beauty of linear algebra, how linear algebra brought this kind of fascinating possibilities to deep learning. And that's all for today, guys. See you in next videos. If you like this video, please press thumb up and share with friends. I'm happy to share videos, and see you next time.